to today's Oracle Machine Learning Office Hour session. I'm your host, Mark Hornick, and today we'll learn about the new SQL API for Oracle Machine Learning for Python Embedded Python Execution, which was recently released for Oracle Autonomous Database. Now, this supplements the original REST API on Autonomous Database, and this new SQL API provides functional parity with the on-premises version of OML4Py, which also provides a SQL API. So your speakers today are Sherry LaMonica from the OML product management team and Akash Dharamshi, a solution engineer with Oracle Analytics. Now, before we get started, I'd like to take a brief poll. And the poll question number one is, which of the following statements best describes your familiarity with OML4Py Embedded Python Execution, or what we abbreviate to EPE? I'm an expert at using Python, SQL, and REST interfaces for EPE is the first option. Or I've experimented with one or more of the EPE interfaces. I understand what it does, but haven't tried to use EPE yet. I could use a better understanding of the EPE basics, or I'm completely new to embedded Python execution. So Sherry, would you please start our first poll question? And if you would be so kind as to give your answer. Okay, we have about half the folks that are completely new to embedded Python execution. A few who understand what it's done, about a 30% there. Some who have experimented with it, and also some who consider themselves an expert. That's fantastic. And some that would just like a better understanding of the EPE basics. Now, I'll turn it over to Akash, who's going to take us through the goals for today and the beginning part of the session. So Akash, to you.
Thanks, Mark. So welcome, everybody. My name is Akash Dharamshi, and as mentioned, I'm a solution engineer here at Oracle. These are the topics that we'll be covering today. We'll start by introducing the embedded Python execution with the SQL API, discuss the benefits and motivation behind this technology, and we'll explore the SQL API features and functions, look at parallelism, then move to a demo and Q&A. So let's proceed to our introduction on the topic of SQL API for embedded Python execution. OML4Py supports scalable in-database data exploration and preparation using native Python syntax, invocation of in-database algorithms for model building and scoring, and embedded execution of user-defined Python functions from Python, SQL, and REST APIs. OML4Py also includes the AutoML interface for automated algorithm and feature selection and hyperparameter tuning. Oracle Machine Learning for Python empowers data scientists with open source environments, and Oracle Database is a high-performance computing environment with in-database, parallel, and distributed machine learning algorithms. Data scientists are able to manage their user-defined functions, called scripts, as well as Python objects in Oracle Database, integrate those results into applications and dashboards via SQL or REST, and utilize OML4Py for automated machine learning. So why should you use the SQL API for embedded Python execution? Specifically, the SQL API enables automated and simplified runtime support of user-defined Python functions. It also offers greater scalability and performance through system-supported data parallelism and task parallelism, which enables scoring third-party Python models at scale. OML4Py Embedded Python Execution also allows users to run Python user-defined functions on Python engines spawned and managed by the database environment. The SQL API for Embedded Python Execution supports the development of Python user-defined functions and applications, developing and testing Python scripts interactively with the Python interface, invoking Python user-defined functions from SQL, and returning structured or image results via table, XML, PNG, or JSON formats. Python scripts are then stored securely in the Oracle database, and OML4Py provides interfaces for setting authorization tokens and running Python scripts automatically via SQL, as well as for synchronous and asynchronous running jobs. Some use cases for the SQL API for embedded Python execution include using open source packages such as scikit-learn to build a model on a database table, score data at scale using the model in multiple Python engines, and storing the results in the database. We can also automate the building of multiple types of machine learning models in parallel and store the results in the database. Partition data computations can build a separate model, compute metrics, or generate plots on each of the customer's data and store those results in the database to access dynamically in applications or dashboards. And lastly, to enable simulations. For example, Monte Carlo methods where data may be generated or selected using a random seed supplied to the user-defined function.
All right, so we're going to go to poll question number 2. And based on what Akasha just told us about use cases, which use case do you find compelling for embedded Python execution? And it should be a multi-select, so select all that apply. Is it automating the running of my Python UDFs in engines spawned by the database environment, sort of a generic capability? Taking advantage of system-provided data parallelism and task parallelism for your user-defined functions? Using a native Python machine learning model to score large volume data? Perhaps it's generating image plots in your user-defined functions and returning them from SQL, or even running simulations like Monte Carlo simulations. And if there's something else that's not mentioned here, please put it in the chat or in the Q&A. Sherry, would you please start our next poll? Okay, we seem to have a good jump for using a native Python machine learning model to score large volume data is really predominant at 74%. We have running Monte Carlo type simulations, about 25%, 41% just like the idea of being able to automate the running of their Python UDFs in engines spawned by the database environment. And about half think that taking advantage of system-provided data parallelism and task parallelism is really important as well. Not so much for generating plots. Only about 8 or 9% of the people are responding in that category. Excellent. Well, thank you again for that. Okay, back to you, Akash.
Great. Let's proceed to the interfaces that support embedded Python execution. Today, embedded Python execution is available on autonomous database through the Python interpreter using OML notebooks or the universal client, through a SQL interface via OML notebooks or SQL developer client, and through a REST interface. On the Oracle database, whether on-premises or database cloud service, you have the Python and SQL interfaces. The Python interface can be accessed through the Python notebook interface of your choice, such as Jupyter or Zeppelin, or even directly at the Linux command line. The SQL interface can be accessed through a SQL client, such as SQL Developer. There are some differences between the Autonomous Database and Oracle Database SQL interfaces, and here we'll focus on the Autonomous Database SQL API, which is new to OML4Py in that environment. So at this point, you may be wondering which OML4Py interface should I use at this time? You can use the Python interface to develop your functions and create reproducible, shareable scripts, and then use the SQL and REST interfaces to deploy these scripts and applications. For example, you can first develop and share your own Python functions, including third-party code in the Python interface, and then leverage the parallelism and scalability of the database through embedded Python execution in Python or SQL. And as a best practice, we recommend ensuring your scripts run from the Python interface prior to invoking them in SQL, as it's much easier to identify and troubleshoot any coding errors directly in Python. Once the Python code is tested, it can be invoked in production and can even be scheduled using DBMS scheduler in the database. So here is an example of the Python interface for embedded Python execution. We will be building a user-defined function using scikit-learn from the OML4Py Python API. The function is predicting petal width and returning a data frame. Model mod was created in Python and saved to data store dsmod. Here, we save the function with the name scoremod to the script repository, so it can be called through either the Python or SQL API for embedded Python execution. We can save Python or OML4Py objects to the data store to be loaded into Python memory later, and we can even save UDFs in the script repository and load them within UDFs or a separate client Python engine. I also just want to note that users can share their UDFs and overwrite existing ones they own. In this example, the script is not being created globally, meaning it's only accessible to the user creating them. And when we save the script to the script repository, we're asking to overwrite any existing script that has the same name. We'll be covering both the data store and script repository a bit later in the presentation. So here is an equivalent way to create the same UDF in the script repository, but using the SQL API. Notice that we are creating and saving the script to the script repository within the PyQ script create function. As mentioned earlier, it's assumed that the code has been tested using the Python interface first, as this simplifies any debugging of the Python code. Also note that when saving scripts into the script repository, they can be accessed by the Python, SQL, and also REST API. So if you have a script using the Python interface, you can call the script from the embedded Python execution interfaces for Python or SQL and vice versa. And again, as with the Python interface, this script as well is not being created globally, meaning they are only accessible to the user creating them. So again, when we save the scripts to the script repository, we are overriding a script already saved there that has the same name. This is an example of parallel partitioned data flow with the Python API. We are using OML.ROApply to score the iris data and invoking our UDF in parallel on the iris table using multiple Python engines spawned and managed by the database environment. We then run an OML.ROApply function on the iris table, pass in our user-defined function scoreMod, and indicate we want 10 rows to be processed per invocation. This is simply a test example. And of course, for real-world use cases and scenarios, we'd likely want to process tens of thousands of rows at a time, depending on the model and data. We then go ahead and specify the return value as a data frame with the species and petal length columns, along with petal length predictions. And this is the corresponding example of parallel partition data flow using the SQL API and invoking the UDF using the PyQ row eval table function. We run a select statement that invokes PyQ row eval, and we pass in the table name iris. In the parameter list arguments, we pass a JSON string with the OML input type as a pandas data frame. We set the OML parallel flag to true, and we set our service level to medium. And as a note, the autonomous database offers parallelism through different service levels. The service levels low, medium, and high control the degree of parallelism for jobs, and we'll cover this more in detail later in the presentation as well. Lastly, we specify the desired output format with species being a varchar and petal length and predicted petal length as numbers, specify 10 rows per invocation, and lastly, the function name, and in this case was scoreMod.
Thanks, Akash. So this brings us to poll question number 3. Which of the OML4Py EPE APIs do you think will be most useful in your organization? You can select all that apply. We've got the SQL, the REST, and Python APIs as choices. So Sherry, would you please start the poll? And if you feel a different language would be useful, please specify that in the chat. Okay, so we're seeing SQL certainly at the top with 80%, Python at 70%, and REST at about half, 50% there. So that's sort of what I would have expected. Okay, thank you, Sherry. And back to you, Akash.
All right, fantastic. So now let's take a look at the embedded Python execution functions that are available in the SQL interfaces. Let's first take a look at the access and authorization procedures and functions that are supported by the SQL API for embedded Python execution. These functions use the Network Access Control List, or ACL API, to control access by users to external network services and resources from the database itself. The PyQ append host ACE function appends an access control entry to the access control list of the cloud host, and PyQ get host ace gets existing host access control entry for the specified user. We can also remove the user by using PyQ remove host ace. Lastly, PyQ set auth token sets the access token in the token store, and PyQ is token set returns whether the authorization token is set or not. Now let's look at the embedded Python execution function supported by the SQL interface. The Python function OML.doEval and its SQL equivalent PyQEval will invoke a standalone Python script with no automatic loading of table data input. However, users can work with data using the transparency layer or load or generate data as needed. OML.tableApply and its SQL equivalent PyQTableEval will invoke a UDF with the table as input in its first argument. These functions in the first two rows do not run in parallel, and they're typically used when it's not appropriate or possible to partition the data to run in a data or task parallel manner. On the other hand, the functions in the next three rows can take advantage of parallelism. OML.rowApply and PyQRowEval can invoke the specified UDF one row at a time. For example, if the function is compute intensive, or more commonly, multiple rows at a time, otherwise known as chunks. Using this function in a single Python engine limits the amount of memory consumed when processing the overall dataset, but enabling parallelism with multiple concurrently running Python engines can reduce elapsed compute time. This is often used for scoring. OML.groupApply and PyQGroupEval invokes a UDF on data aggregated by one or more grouping columns, such as color or state. And finally, OML.indexApply and PyQIndexEval will invoke a UDF n times, and it's often used for simulations. The first argument to the UDF will be the index of the invocation. This index can be used to set a random seed. Lastly, let's look at asynchronous jobs functions supported by the SQL interface. The OML async flag function determines if a job is running synchronously or asynchronously. By default, PyQEval functions run synchronously. To run a function in asynchronous mode, we can set the OML async flag to true. In asynchronous mode, the SQL API returns a job URL directly after the asynchronous job is submitted to the web server. The URL contains a job ID, which can be used to fetch the job status and result in subsequent SQL calls. The default mode is synchronous, so if there is a longer running job, we're going to want to set the asynchronous mode to true. The PyQ job status function looks up the status of an asynchronous job. If the job is completed, the function returns a URL pointing to the job's result. And finally, PyQ job result returns the job result itself. And so I would like to hand this over to Sherry to explain the script repository and data store, dive into parallelism and load management, and proceed into the demo. Welcome, Sherry.
Thank you, Akash. So let's talk more in detail about OML4Py script repository and data store and how they work with embedded Python execution. The script repository is a database table that stores the user-defined Python functions that are invoked from embedded Python execution. These scripts are stored securely in the database, and special privileges are required to create a script. In autonomous database, OML developer role is required, which includes access privileges like PyQadmin for creating scripts and the DBMS Cloud package, which provides support for working with data and object storage. Scripts can be created as private to a specific user or globally available to all database users. A private script is available only to the owner, and a global script is available to any user in that database. For private scripts, the owner of the script has the ability to grant read privilege to other users or to revoke that privilege. And these are the functions available for managing scripts in the database using Python and SQL interfaces. You can create and drop scripts in the script repository. You can also load functions from the script repository to a Python session, and you can list the scripts available to you, those that you have created, and any scripts shared with you by another user. So back to the OML4Py data store, let's talk about what it's used for and its benefits. It provides a repository in the database environment that allows storage and management of Python and OML4Py objects. With the data store, you can share these objects with other data scientists and analysts. It serializes and unserializes these objects during the save and load steps. Perhaps most important is that the objects in a data store can be passed to the user-defined functions invoked through embedded Python execution from the Python, SQL, and REST interfaces. But this is most important for the SQL and REST interfaces, since only scalar values like numbers and strings can be passed. Data store objects can be managed from Python and SQL APIs. Here are the available functions. For example, you can save objects to the data store and load the objects back into functions across sessions. There are also functions to list and describe the data store contents, and also to delete a specified data store. And finally, before the demo, let's look at parallelism with the OML4Py SQL API for embedded Python execution. Embedded Python execution provides parallelism to enable greater scalability and performance through system-provided data and task parallel functionality. Autonomous Database offers parallelism through different service levels. The service levels are low, medium, and high, and they control the degree of parallelism for jobs. So the degree of parallelism used by embedded Python execution corresponds to the service level. Note that parallelism is only applicable to PyQ row eval, PyQ group eval, and PyQ index eval. And when functions run in parallel, a single Python engine is spawned to process the request until all of the data chunks and groups are processed, or in the case of index apply, all the invocations have completed. Okay, so let's go to the demo. Here is my notebook. So this notebook covers the OML4Py SQL API for invoking embedded Python execution. It's an end-to-end workflow. So you're going to start, as Akash had mentioned, your admin is going to add your OML user to the cloud host ACL list using this PyQ append host ACE function. So it takes the parameter, two parameters, the OML user and then the data center region. And then they can actually confirm using the PyQ get host ACE function that the user does contain a host ACL list entry. These two steps would be done outside of an OML notebook in an admin-based SQL developer session. So maybe you're a SQL developer in the cloud, or even your local SQL developer connected to the autonomous database with a wallet. The next step in the workflow is to get an authorization token. And to get the authorization token, there are three pieces of information that you need to have. You need to have your Oracle Machine Learning username and password, and then your Oracle Machine Learning cloud service URL. And you can get this, I have all the instructions for you here to make it very simple, but you can get this from the Oracle Machine Learning Service Console in the development area. There is a tile for the Oracle Machine Learning RESTful services, and one of them is the token URL that you would use here. And so here I'm getting the token in a curl call. I'm passing my OML server URL and username and password as variables, and then sending the curl request to get the token. And this is a shortened version of the token that is returned. And once you have the token, you'll cut and paste it into your session here, and you can do it from a client SQL developer as well. And you'll set that with the PyQ set auth token command here, this procedure. And once the token is set, which you can confirm with PyQ set auth token, it's good for an hour, and you can refresh that token before it expires. And you can extend it several times. I think it's up to 8 hours. Okay, so for our example here, we're using the iris data. I'm loading the iris data to a database table and then obtaining the OML data frame proxy object. I have created the local iris data frame and then the proxy object, capital iris, and we show that there. Okay, so Akash had covered this. We create a Python script and save it to the OML4Py script repository. So this example is just returning the categories for the species column in IRIS. So there are 3 categories there, versicolor, virginica, and setosa. And each one of them has 50 rows. So we first run this in the Python interface for embedded Python execution using OML group apply, indexed by the species column, and we pass that group count function to OML group apply, and we can see that the 50 rows, or each category and species has 50 entries or rows, and that is returned by the OML group apply function. So that's the basis for our next examples. We're then going to save this group count, user-defined group count function, to the Python script repository. And the way that we do that is by saving it as a named string. And in our examples, we're always saving the string as the same name as the function, just for clarity. So you can see that I define the function group count as a string, and then I'm saving it to I'm dropping the script if it exists, and then saving the script to the script repository, and then invoking it. Oh, and then I can view the Python script in the script repository. So you can check for the existence using OML scripter by passing the name of the script to that function. And you can see that it's there and the date it was created. So now the equivalent to group apply is this PyQ group eval function. And this is basically the heart of this session. Is we are going to run this from the SQL interface for embedded Python execution in OML4Py. And we're going to, again, it's the same invocation. We're going to group by species, but we're going to set the OML parallel flag to true to leverage database parallelism. In the group apply example, we should have set parallel to true explicitly. So the flag is parallel equals true. And then for PyQ group eval, we set OML parallel flag to true. And then I have showed you here that we have several different output formats. So you can, our example is going to show the output as a relational format, but you can also return a JSON string, an XML string, or PNG image, or asynchronous mode output. And we also list the type of supported outputs that the function can have. So again, the default SQL API execution mode is synchronous, but we'll show an asynchronous example a little bit later. We have, we're doing a select on the PyQ group eval. The input table is iris. The parameter list here shows the type of input that we've set OML parallel flag to true using service level medium. And then we're specifying the output format in relational format. We're grouping by column species. We could order by a specific column if we wanted to, but we're set that to null because we don't have an ordering column, and then passing the script name as group count. And this is the result. For asynchronous jobs, the only difference between the synchronous and asynchronous invocation is that we are going to set this OML async flag to true. Everything else is the same, including the input table, the parameter list, and the output format. In this case, for asynchronous, I'm actually going to set this to null when I'm invoking the function, and then when I fetch the results, I will specify the output in relational format, as you'll see here soon. So the output from this includes this job ID. So this thing at the end, this is the URL that contains the job ID. So it's right after this jobs, it's that string. And now that I have a job ID, I can actually pull the status of that job by invoking the PyQ job status function and passing that job ID. Now, if this job were still running, the output here would be job is still running. But because it's finished, it actually returns the result, the location URL for the result. And I can fetch the result by running a select statement with the PyQ job result function. And I pass the job ID again here. And as you can see, the out format is set to relational format. But as I said earlier, you can also have JSON output or XML or PNG if you're returning an image. Next, we're building an open source model using embedded Python execution. So I'm using scikit-learn, and then we're going to run this from the Python and SQL APIs for embedded Python execution. So this is build LM. It builds a model, it stores the model in the data store, and then it returns the coefficients of the predictors in a data frame. So you can see the OMLDS save is saving that model RAGR regression to the data store. This function also has an input parameter, DS name, so we can name the data store name that we're saving it to. So we use OML script create to save the function in the script repository, and then invoke the build LM function that resides in the script repository on the iris data from the Python API for embedded Python execution, passing data store name DS1. And we see that the return value is, as we expect, it's a data frame containing the coefficients of the predictors. And you can use the OMLDS describe function to look at this object in your data store. So in this case, I'm passing the data store name, and I'm returning just the object and class attributes that are there. So we can see the object name is regression, and it's a linear regression object. You can also do this from the same thing. You can look at this object in the data store from the SQL API by just querying the user PyQ data stores view. And this is a good time to mention, because we haven't mentioned it already, that you can create your function using either the Python or SQL APIs and run them from either the Python or SQL APIs. You're not tied to one interface. Okay, so now we're going to invoke the build LM function by running a select statement on a PyQ table eval. So we have the input data, which is iris. That specifies the iris table as the data that we want to pass to the function build LM. We have the parameter list, this time specifying a different data store name, which is DS2. The output format is the same as our previous invocations, and the script name is passed to this parameter right here, and we can see our results. And we can also, again, take a look at that model in data store DS2. Now we're going to run the exact same function again. This time we're returning the output as a JSON string right here, and storing it in data store DS3. You could, of course, use the same data store as well if you wanted to. You could, like, for example, you could save this to data store 1 or 2, and then we show the output as an XML string. So out format is set to XML. Then we go ahead and define a scoring function. So score mod, we cast that as a string and save it to the script repository. This function is loading the data store using OMLDS load. So it's going to load that data store into the function, and so that we can load that model and do the scoring. Then we run the scoring function first in the Python API, just to show you what that looks like through OMLRowApply. We're scoring the model on the iris data and 50 rows at a time, setting parallel to true. So if you have your service level set to medium or high, parallelism will be enabled, showing the result. And then this is the equivalent invocation from the SQL API for embedded Python execution. Just note that we're loading the data store from DS1. We have to set OML parallel flag to true, and then the corresponding service level that we want, 50 rows per invocation, relational output format, and that's the name of your function in the script repository. And then finally, for PNG output, if the output format is set to PNG, the embedded Python execution function can return the image in the function call. So the key here is that you should set OML graphics flag to true, and you can get the PNG image rendered back into your session. This is just a simple density plot example. I'm obviously saving that to the script repository and then invoking it through PyQ table eval. And that's all I have to show you today. Let's move to the Q&A.
Okay, thank you, Sherry. We had a few questions that have been answered in the Q&A. If there are any additional questions, please post them there. But just for everyone who might not have seen those, I'll go through them. Vitor asked, is there any native integration with OCI Data Science? For example, data scientists are using OCI Data Science to develop and publish models, but want to deploy it in database using Autonomous Data Warehouse to improve performance directly from OCI Data Science. And so the OML4Py client, which we also released just earlier this year, can be installed on OCI Data Science, and later it will be included by default, so you can just use it without any explicit installation. But users could build Python models and store them in the OML4Py data store. And as Sherry had demonstrated, then you can use those for scoring using multiple Python engines with the row apply functionality. The main item there is, which packages can you use for that? And on Autonomous Database, you do have access only to those packages that are pre-installed. So algorithms, say from scikit-learn or using matplotlib, and there are a few others. We will be extending that going forward to allow users to have custom packages. That's a roadmap item for later this calendar year. There was a question about API documentation, and I posted that in the Q&A. So if you're interested, you can click on that. And another question was, what are the Python packages we can use for UDFs? Is it a fixed list, or can we install additional ones? And I believe I answered that just a moment ago, where today on Autonomous Database, we do have a fixed set, but you will be able to extend that in with our roadmap item for later this year. And of course, on OML4Py Embedded Python Execution for on-premises or DBCS databases, you can install whichever packages that you'd like. And the on-premises and DBCS databases can take advantage of the Python API and the SQL API specific for those platforms. And let's see, was there one other question? Which versions of the database is Embedded Python Execution available to run, whether it be Autonomous Database or Oracle Database? And so OML4Py in general is available for 19C and 21C, both on Oracle Database and Autonomous Database. And that includes Embedded Python Execution. So you can make use of that. All right, so I'd say we're all set. I thank you all for attending, and thank you, Sherry. Thank you, Akash, for a great presentation and demonstration. And until next time.